Welcome to qnawire.
The equation of motion for the mass attached to the spring can be obtained using Hooke's law, which states that the force F required to stretch or compress a spring by some distance x is given by F equals kx, where k is the spring constant, which is the measure of the stiffness of the spring. In this case, the force acting on the mass is the force required to stretch the spring, which is 400 newtons. The displacement of the mass, which is the distance the spring is stretched, is 2 meters. So the spring constant for this spring will be k equals F over x, which is going to be 400 over 2, which is 200, and that would be then newtons per meter. The equation of motion for the mass can be obtained using Newton's second law of motion, which states that the force acting on an object is equal to the mass of the object times its acceleration, where F is the force acting on the object, m is the mass of the object, and a is the acceleration of the object. And in this case, the force acting on the mass is the spring force, which can be obtained using Hooke's law. We said it was 200 newtons per meter, so that would be equal to 200 newtons per meter times x. And substituting this expression for F into Newton's second law and rearranging, we would get ma equals kx, and so a would be equal to k times x over m. The equation of motion for the mass then is a equals 200 times x over 50 kilograms. And this equals negative 9.8 meters per second squared for acceleration due to gravity, and therefore x would be equal to negative 9.8 meters per second squared times 50 kilograms over 200 newtons per meter. And this will calculate to negative 2.45 meters. The displacement of the mass is negative because it's moving downward. So the displacement is 2.45 meters downward from the initial equilibrium position.